And now we'll check our broadcast queue. Notice the multicast pings are now being saved up in the broadcast queue. There are 190 now. Every second, another multicast ping is taken out of the queue and sent. You see the queue size is now down to 177 packets, down to 171. Also notice that none of the packets are shown as dropped. They're being doled out from the queue. Over on R2, we're debugging ICMP. The pings are coming in at a rate of about 1 per second, and they will continue to do so until the broadcast queue is emptied. When you set a broadcast queue limit, broadcast and multicast packets sent on that interface have priority. In addition, the broadcast queue buffers and shapes the traffic to the configured limit. In this presentation, we demonstrated 5 methods of implementing priority queues on frame relay. Simple and low latency queuing match on traffic characteristics. The former uses priority lists, and the latter uses class maps to identify priority flows. Both can be configured on interface or shaping queues. Unlike simple priority, LLQ does not starve lower priority queues. DELCI priority and PIPQ are methods of prioritizing PVCs rather than individual flows at the interface level. With DELCI priority, PVCs must be on the same subinterface, while PIPQ permits them to be on different subinterfaces. Finally, we looked at the frame relay broadcast queue as a method of both prioritizing and shaping broadcast and multicast traffic. Starting in iOS 12.12t, Cisco enhanced the frame relay switching capabilities of its routers to support traffic policing and congestion management on switched interfaces. In this presentation, we will show you how to use the traffic policing feature to drop or to set the DE bit on out-of-profile traffic. We will also demonstrate how to set the beckon and fecken bits on the switch and implement adaptive traffic shaping. The lab we will use to demonstrate these features has a traffic generator at IP address 10.1.1.1. It is sending a stream of UDP packets through R1 and across the frame relay network to R2. This stream of packets averages about 250K, but ranges between about 184K and 288K on a random basis. We have set the clock rate on the link between FRS and R2 to 250K. So port S1 on FRS will experience congestion during traffic bursts. R2 will respond to some of this traffic with port unreachable messages. This return flow will be used to signal adaptive shaping to R1. For our first demonstration, we will police the traffic inbound FRS serial 0. Before we do, let's take a look at the flows in and out of FRS. Here's the current rate of traffic inbound serial 0. At the moment, it's about 247K. Let's take a look at the traffic going out S1. And it's about the same at 248K. Notice that these are 30-second averages. The traffic input and output will be about the same, except when the input rate exceeds 250K, which is the maximum output rate on S1. Let's take a look at the output buffer on S0. When a burst of traffic exceeding 250K arrives, it is buffered on S1, and then dropped when the buffer is exceeded. We'll take a look at the output queue on S1. Note that at the moment there are no packets in the output queue. The queue size is 64 packets and can be configured up to 1,000 packets. Up to this moment, over 9,000 packets have been dropped. Let's take a look at this at a couple of different times. Here you see 24 packets in the queue. So at the moment we're suffering a burst of traffic on S1 above its capability to send. Let's take another look. And the rate has decreased below 250. We are emptying the queue down to 4 now. And let's take a final look. The queue is now empty, so we are sending traffic out S1 at a rate below the clock rate, which is 250K. The first step in policing is creating a map class with the CIR, the committed burst, and excess burst parameters. We're going to call our map class police-R1. We set our CIR to 56K, our committed burst to 9,000 bits, and our excess burst also to 9,000 bits. Next, we apply the map class to the incoming interface and activate the frame relay policing feature. First, we go on to interface S0, apply our class map, and then activate the policing feature. Now we clear our counters. Now that we've applied policing on S0, let's check our input and output traffic rates. Here's the traffic coming in S0. At the moment, it's at about 226K. Let's see what's going out S1. Notice it's only about 110K. Just to check that again, let's take a look at what's coming in S0, about 234K, and what's going out S1 is still only about 110K. Note that this output rate is about twice our CIR value. We can get more detail on the policing from the command showFramePVC102. At the bottom of this output, we see that policing is enabled. And we have set a total of 1,250 bits to DE, that is, discard eligible. Over to the right, you see the total of 2,993 packets have been dropped. Some of these packet counts are approximate and don't actually add precisely. Down at the bottom here, you see the in-BC packets. This is the number of packets that arrived that could be serviced by the committed burst bucket, that is, the number under 56K. The in-BE packets are the number between 56K and 112K. These are the packets that needed the excess burst bucket in order to be sent. These packets were marked discard eligible. Finally, you see the in-excess packets. They total about 3,000 here. These are the packets that were over 112K and were dropped. Note that in frame relay traffic shaping, the excess burst bucket is filled only when the sending rate is below CIR for a while. In frame relay policing, this is not the case. Our arrival rate never went below about 180K, yet the excess burst bucket remains available. In frame relay policing, we have what is called a two-rate marker. We have a CIR here of 56K and an independent EIR, or excess information rate, of 112K. Traffic up to CIR conforms and is sent. Traffic between the CIR and EIR exceeds and is marked DE. Traffic over the excess information rate is simply dropped. Let's take another look at these numbers. Note that now we have 2,336 packets conforming, close to the same number, 2,200 exceeding, and over 5,000 were dropped. To make our lab more interesting, we have added R3 to the mix. It is receiving a UDP stream from the traffic generator and passing it on to R2.